All right, let's go ahead and get started again. If you remember last time, we ended with a beginning discussion of nucleophilic aromatic substitution, which we said was another reaction that aromatic compounds underwent. That unlike electrophilic aromatic substitution, this was a reaction that's not as common because it had some strict requirements. If you remember, those requirements were that you had to have an aryl halide, and that you had to have an electron withdrawing group ortho and or para to that aryl group in order for it to be activated for this reaction. And then we talked, about an example of that, but then we went to the mechanism. We said, what would be the mechanism of this reaction? Because instead of the ring acting as the nucleophile, reacting with an electrophile, which is what we saw with electrophilic aromatic substitution, now we have kind of the reverse reactivity. I guess not kind of, the reverse reactivity, where we have a nucleophile that's got to come into the ring. So the ring is now electrophilic. Okay, and so mechanistically, how would this work? Well, we talked about the fact that the only substitutions we know about thus far were SN2 and SN1. And we looked last time at the fact that neither one of these could be the mechanism by which this reaction occurs. So how does this happen? Well, it happens through a mechanism that we will call addition elimination. So addition elimination. And that's basically tells you up front that this mechanism is going to have two steps. There's going to be an addition that initially occurs, and then an elimination that occurs. And we know from our experience with electrophilic aromatic substitution that that elimination is going to most likely do what? Restore the aromaticity. Okay, so mechanistically, here's what happens. And again, draw this ring exactly like I am so we can get the electron pushing the same. So you have your aromatic ring, and we're going to put a chlorine on there, so it's an aryl halide, and then we're going to put a nitro group on there. So I have an ortho electron withdrawing group. So I have the strict conditions are met here for us to undergo this reaction. And then I'm going to react it with a strong nucleophile, in this case, OH minus. And so what's going to happen is this nucleophile is going to come in and react exactly where you think it would, at that electrophilic site. The chlorine is by far the most electronegative thing on that ring. So this carbon is going to be the most deficient. And so when this comes in and reacts at that position, it's going to kick these electrons out to that carbon. And the result of that is going to be this intermediate. And you're going to see it's kind of similar to what we saw with electrophilic aromatic substitution in the sense that we are going to have something that's resonance stabilized, but now it's a minus charge that's sitting here. Okay? Now notice that minus charge is comfortable there because you have an electron withdrawing group. It's pulling electron density out, right? So that minus charge is actually kind of stabilized. But you're also able to resonate. There are two other resonance forms you can draw, exactly like in electrophilic aromatic substitution. Only difference is this is a minus, not a plus, because the reactivity is opposite. So you could imagine having the resonance form where the minus charge is there and when it is there. So you can draw two more, and you will draw two more when you're doing this on a test. So that's the addition portion of the mechanism. And then what happens, you can imagine this is the slow step because I've broken the aromaticity of the ring. And so now I'm going to do an elimination where these electrons move back in, and I kick off now the leaving group. And so the result of that, I'm going to close my brackets here because I know y'all are going to fill in the other two resonance forms there. And you're going to basically restore the aromaticity when you do that elimination. And by the way, this intermediate does have a name. It's the Mesenheimer complex. And that's not really important because, you know, they don't name things after people anymore. But just for fun, Mesenheimer is kind of a fun name to say. So you can walk around talking about the Mesenheimer complex. Okay, now there is going to be another, since we're doing a mechanism, we have to keep up with the fact that there is going to be a Cl minus, a leaving group that is left. Okay, and so when you look at this mechanism, we can see clearly why it's addition elimination. We can see how it in fact goes in a substitution-like mechanism because the nucleophile is substituting, and I'm sorry, I put a chlorine there, it should be an OH. I have substituted this nucleophile for where the halide was, okay? But the question we still have to answer is, why do we need a nitro group or an electron withdrawing group, ortho and para, to the halide? What is it about that? Well, it must do what? It must somehow stabilize the intermediate in this reaction, the Mesenheimer complex, because that would facilitate the reaction occurring. So let's look at that mechanistically. And this will be similar to what we did with electrophilic aromatic substitution, where we looked at orientation effects. So we're going to look at a case that we just did, where we have a chlorine and a nitro group, where the nitro group is ortho. Okay, so we already know that it's going to do this addition elimination. So I'm going to draw my OH minus again. And that's going to come in and react at that electrophilic site, kicking these electrons out to this carbon. So I'm going to go ahead and skip to this intermediate, but I'm going to draw out the nitro group too. So I have added the OH to that position where the halide was. I've moved my electrons to this carbon, all right, and I have a nitro group attached. Now, a second ago, I mentioned the fact that having that nitro group there kind of stabilizes because that you have a minus charge on this carbon, and this is an electron withdrawing group. So it's pulling electron density away from the ring. And how is it doing that? Well, it's doing it inductively, but it's also doing it in a resonance manner, right? Because I can imagine moving these electrons out towards the nitrogen and kicking these out. Remember when we did this with electrophilic aromatic substitution? And that's going to result in another resonance form, where I'm able to resonate the electrons from the minus charge out into that nitro substituent. It'll work the same for any electron withdrawing group. And so I'm adding another resonance form where the ring is stabilized by moving those electrons out into the substituent, delocalizing electron density. Okay? And so that is why, and you could draw the same thing if the nitro group is para. It's the same deal when you do your three initial resonance forms. One of them will have the minus charge on the same carbon as the nitro group, and you can resonate the electrons out. So that is the explanation for why you need an electron withdrawing group ortho and or para to the aryl group for this reaction to occur. Now again, you know, we're not going to see this reaction very often because it has strict requirements, and it's not as common as electrophilic aromatic substitution. So all you need to look for on an exam is when you see, instead of your normal electrophilic aromatic substitution reagents, if you see a nucleophile sitting there on your arrow, then you become suspicious of nucleophilic aromatic substitution. So then you look at the ring to make sure it's an aryl halide and has an ortho-para electron withdrawing group. Okay. Now there is another thing that can happen. Let's say that you have an aromatic ring and you have an aryl, you have a halide attached to your aryl group, so you have an aryl halide. You can treat this, it has been shown, under really harsh conditions with a nucleophile, something like sodium hydroxide, which remember is always aqueous, 340 degrees Celsius, 2,500 psi. So those are pretty harsh conditions. I've got a strong nucleophile, high temperature, high pressure, and then I work that up with aqueous acid, and I can in fact see some product form where you have the nucleophile that is substituted for the halide. Now, it doesn't require the same strict presence of an ortho-para electron withdrawing group in this case, and it's not just the fact that these conditions are harsh. This is going by a different mechanism. It does not go through that same mesenchymal complex. Okay? And so to postulate that, what could be happening if you're not going through a mesenchymal? What else could be happening? Well, you're treating this with a strong base, and you have, let me put my double bonds like this. I'll let you catch up to that. So you're treating with a strong base. What are the two things that can happen? The nucleophile, which is a base, can act as the nucleophile and do the substitution like we saw with the mesenchymal. But what else can strong bases do? They can do eliminations. And so basically what happens in this case is the OH minus acts as a base. And it pulls off that proton, moves these electrons in, and kicks off the chlorine. So this is kind of E2-like. It's not a substitution. So actually this mechanism is an elimination first. Okay, and the result of that, when you did your intermediate, would be this. And that is called a benzyne intermediate. Because, benzene, benzyne, right? Because there's a triple bond there. Once that benzyne forms, it's a pretty fleeting existence. And then you can treat it with something like water, which is present after the base has done the elimination. You have water, right? OH minus picking up a proton, it's water. That water then just adds across that pi bond of the triple bond. And the result of that is, I know that you have the power, I can erase this quickly because you have the power to pause this as you're watching it. If I'm adding water across that, then what happens is I'm adding OH and H across what was that triple bond, and I end up forming what is actually the substitution now. But this is an addition that occurs. So the first one was addition, then elimination that yielded the substitution product. This is elimination, then addition that gives the substitution product. Okay? Now, how can you determine whether that is in fact the mechanism that occurred? Because you can imagine if, when I first showed you the benzyne intermediate, you may have thought that looks like a crazy structure. How can I throw a triple bond into that ring? Because the triple bond wants to be linear. You're forcing it to be in a cyclic system where the bonds are bent. Well, you can do some proofs for this mechanism. And those of you that have ever looked at what my research interests are, part of it is reaction mechanism elucidation, figuring out the mechanisms of the reactions. Does that surprise you that would interest me? The proof for this is you can actually take an aryl halide like this, and just think about what might be useful to go towards establishing that is in fact the mechanism. What you can do is you can label one of the carbons as a C13, because you can have people that know how to make these things. So all of the other carbons in here are your normal C12s, but this carbon to which the halide is attached is actually a C13. So it's called labeling it. It's labeled. So we can tell the difference between that carbon and all the other ones. And how could we tell the difference? By NMR. If we ran an NMR on this compound, that carbon would be huge because it would be nearly 100% C13, where the others would be only the 1.1%. Okay? And so if you take that and you react it with a strong base, and let's use NH2 minus in ammonia, okay? And we're going to then, if this mechanism is correct, then what will happen? We'll form our benzyne where one of the carbons is labeled. Then, when the ammonia, I'm going to draw it out like this, when the ammonia adds across that bond regiochemically, there are two ways it could add, right? The NH2 could add here, or it could add here. If it didn't go through elimination addition, if it went through the other mechanism, which was addition elimination, and went through the Mesenheimer, remember the nucleophile always ended up on exactly the same carbon that the halide was attached to. Mechanistically, there's only one regiochemical product. Well, here, if it goes through a benzyne, you should get two. And in fact, you do. You get one product where the NH2 is on the labeled carbon, and then you get the other product where it is on the other. The only way that could happen is if it went through something different than the Mesenheimer complex, and certainly a benzyne intermediate would establish that. All right? So did we prove the mechanism? No, but we gave experimental evidence that supported it. And hopefully you remembered that benzyne thing, so I can just show you something I'm drinking my coffee out of. Let's see if I can hold this up. Porcupine, porcupine, porcupine. Somebody gave that to me. I may have already shown you in class, but that's pretty bad chemistry humor. All right. So the next thing we want to talk about, we've talked about all the reactions that occur in the benzene ring. So we've talked about the electrophilic aromatic substitutions, and now we've talked about nucleophilic aromatic substitutions, and you just have to recognize these based on the conditions of the reaction. When you look at the arrow, is your ring reacting with electrophiles or nucleophiles? Okay? But there are some other reactions we need to talk about at this point, and oxidation of the side chains. Is the first thing we want to talk about. And that's a situation that you might want to put under synthetic utility, because we're going to talk about what happens if I have, in this case, alkyl substituents. They can be oxidized. And so when you have a system like this and you have this alkyl group, you can take this and react it with potassium permanganate, which we've already talked about previously as being a strong oxidizer. So potassium permanganate in water, and it's going to require some heat. Okay? And when you do that, you oxidize that alkyl group to the carboxylic acid. Remember, this is kind of, if you remember cleavage reactions that we did on alkenes and alkynes, where permanganate gave us carboxylic acids. So it's kind of the same thing here. Okay? And so that reaction can synthetically be really important because it's a way of making benzoic acids synthetically. If you're able to put R groups on your ring, then you can oxidize them. But here's the thing. You're only oxidizing at what's called the benzylic position. So look at this example. Doesn't matter how long your alkyl chain is. If I react this with potassium permanganate, water, and heat, so the conditions to oxidize that alkyl group, it only affects this, what's called the benzylic position, that is once removed from the aromatic ring. And so what it's going to do is, I like to think about it as an oxidative cleavage, because it gives the carboxylic acid, and it always gives benzoic acid. It doesn't matter how many carbons are out here. It's only that benzylic carbon that gets oxidized, and you lose any other carbons that are attached. Okay? Now, mechanistically, it's not really completely understood what's happening here, but what is known is that there has to be a benzylic proton for the reaction to work. So that means on that benzylic carbon, you have to actually have a hydrogen. So for example, if you had this tert-butyl group attached to your aromatic ring, here your benzylic carbon has no H. And so therefore, if you went to try to do this oxidation of that position, you would get no reaction. Okay? So the reaction, if it has the benzylic proton, it'll actually give you the benzoic acid. If you don't have it, it gives you no reaction. So there are really only two possibilities. Okay? Next oxidation that can occur on a substituent of the aromatic ring is bromination. And again, this is going to happen in the benzylic position. So if you have this alkyl benzene, you can react it with NBS. Now, do y'all remember NBS from before? NBS was what we used with allylic bromination, and it's very closely related to this, because benzylic carbons, this is very much like allylic, because here, here you have a double bond. This would be vinylic. This is allylic. It's just benzylic here because it's got the ring, but it's the same kind of reaction. This is a source of bromine, right? And so the result of this then is that you oxidize because you're removing a hydrogen and you're replacing it with a bromine. So the bromine regiochemically only goes to the benzylic position. Okay? Now, could this be a synthetically useful reaction? Yes, we know how to put alkyl groups on a benzene ring. Now we know how to put a bromine on there. Once you have the bromine on there, there's all kinds of chemistry we can do. Now, you could eliminate it and get a double bond there, which you could then do chemistry on. You could do substitutions, SN1 or SN2 in this case on that position. So you're making a synthetically useful intermediate if you're able to do that. Okay, so these are the oxidations that we can do. The next thing we want to talk about is reductions. And let's just say reductions of aromatic compounds. So oxidations, remember, where you remove H's and add things like oxygen and bromine. Reductions are where you're adding H. And so we were doing reductions, for example, when we had alkenes. Remember, when we were adding H2 with catalysts across it, that's a reduction. So that's the kind of thing we're talking about here. So the first case is a catalytic hydrogenation. And remember, these were the reactions that were done in the outhouse out behind the chemistry building. Okay? And so, let me make sure that I'm going in order here. if you have a benzene ring and you have this alkene functionality attached, and here I'm also adding a carbonyl, which is a double bond, and we're going to find out later that those can be reduced, but not by these conditions. So our good old familiar H2 and catalyst is going to do a reduction. But benzene rings, remember, are really stable. So they're not reduced by these normal conditions. So none of these double bonds will be reduced. Carbonyls like this are not reduced under these conditions either. So the only thing here that gets reduced is the normal alkene functionality. So when you do this reaction, you'll reduce a double bond in the side chain, but it'll do nothing to the double bonds within the ring or the carbonyl that's there. So again, synthetically useful reaction, maybe. But what if you wanted to reduce the double bonds within the benzene ring? Well, there's no way you can do it with these normal palladium platinum catalysts. And so you might think one way of doing it is to make the conditions stronger, harsher. So let's just say you had this xylene compound where we had two methyl groups attached to the benzene ring. I can treat this with hydrogen gas and platinum catalyst or palladium catalyst, but I've got to have really high pressures, 2000 psi of hydrogen pressure in order to reduce those double bonds. Now, do you remember me talking about, when you do these hydrogenations, you do them in the outhouse out behind the chemistry building? It's a dangerous enough reaction. Now, normally you're doing it at something like 60 psi, but going to 2000 psi, you're making your bomb even stronger. So this is not a very useful reaction. You can force it to go with high pressures, but there's another way of doing this. And I'm going to use the same example. So if it's not using the same catalyst at harsher conditions, what's the only other thing you could change? It's going to require hydrogen gas, but let's use a different catalyst. Let's use rhodium absorbed on carbon. So rhodium as a catalyst. If you do that, you can do it at normal atmospheric pressure and at room temperature, 25 degrees Celsius. And the result is the complete reduction of the double bonds in the ring. So if you want to afford this reduction, rhodium catalyst is the way to go. Now these catalysts are really expensive, so they are catalysts. Often you save the catalyst so you can use it again and again and again. But that's the only catalyst that really works well at normal conditions. Okay, so you can reduce the double bonds within the benzene ring doing this. Now there's also another reduction that works on the double bonds in the aromatic ring, but it's not a complete reduction. It's a partial reduction. And it's actually named after somebody, because there was a time when someone would develop a reaction that actually got named after them, the Birch reduction. And the Birch reduction is going to be related to a reaction we talked about last semester. You have your benzene ring, and I'm going to treat it with lithium and liquid ammonia in ethanol. Now, who remembers when we saw those conditions before? Remember, it was my favorite mechanism, the one electron transfer. Right, is where you had the alkyne and you reduced it partially to get the trans alkene instead of the cis that you would get from the Lindlar catalyst. So this is a good time for you to maybe go back and review the difference between those two. But anyway, this is the same condition. So mechanistically, it kind of occurs the same way. And the result of it is a partial reduction. And this is kind of interesting because it's really only reducing one of the double bonds in the benzene ring. And so it's leaving a diene. But notice that the double bonds aren't in conjugation. That's just really weird, but it in fact works. Okay, it just kind of goes against intuition, but the Birch reduction occurs. And just because some of you are looking at me like I'm crazy, compare this to, and I'm putting brackets here because this is just an aside, go back and look at this. Remember, we used these same conditions last semester. To reduce an alkyne to give the trans alkene. Okay? So mechanistically, if you were asked, it is exactly the same as this mechanism. I know you remember that, so there's no reason to go back over that. So what do we need to talk about with the Birch? Well, there is one problem. The Birch reduction does give mixtures of things. And so let's just say we have metaxylene. I'm going to put in my double bonds. There's a regiochemical result if I'm leaving two double bonds, because when I do the reduction of this, I can get more than one product based on these regiochemical markers that are on the ring. And so if I treat this with the conditions for the Birch, then I can get this product. Or I can get okay, and if you play with this at home, you'll see that those are the products that can form. And so the question is, if I'm getting two possible products here, what do we always think about? What is the major? And when you look at that, what's the major product? Right, this one down here, because tri-substituted, double bond, tri-substituted, oops, di substituted. So the double bonds in this one are more substituted. So again, the Birch reduction, you get mixture of products. All you really do is look at which of the possible products has the more stable double bonds. All right. Now there is one little freakish regiochemical thing with Birch reductions, and it's a very specific case. That is when you have OR groups attached. So you have an oxygen as the atom that's attached into the aromatic ring. When you do a Birch reduction of this, okay, you're only going to get one product. And it's always going to be the product where your R group, your OR group is vinylic. It's actually attached to a carbon that has a double bond on it. You're not going to have a case where the OR group is off of an sp3 hybridized carbon. Okay? And you don't have to know the mechanistic explanation of that. All right. Next thing is the reduction of aryl alkyl ketones. Now we're going to have to look here at the subtlety of the position of the carbonyl, because we've already looked at a case where we did, remember, the reduction of the alkene on that substituent where there was a carbonyl and nothing happened. But watch this reaction. Aromatic ring. And we have an aryl alkyl ketone, which means my ketone has a benzene ring and then some R group on it. Okay, that's aryl is this part, alkyl is this part, ketone is this part, right? And I'm going to take this and I'm going to react it under normal hydrogenation conditions. Hydrogen gas, palladium catalyst. And what will happen is I will reduce the carbonyl. So there are 1, 2, 3 carbons. 1, 2, 3. All I've done is reduced the carbonyl. Okay? And so why would this carbonyl be reduced where the one we saw earlier in the lecture was not? What is the difference between this carbonyl? It's the position. This carbonyl is in the benzoic position. It is once removed from the double bond. So its reactivity is different. Here, it can be reduced under normal conditions. And this is really interesting because we've seen this same reduction before. Do you remember the Clemenson? It did the same thing, didn't it? So this is another reaction that does the same thing. And that's important to know because look at a situation like this. Remember when we had, in that past example, when we were doing a Friedel-Crafts acylation and we wanted to remove the carbonyl and we used Clemenson, that was a synthetic utility. Well, now we can use catalytic hydrogenation. But there is a limitation to it that you don't have with the Clemenson. And that is, let's just say you have a nitro group. And in your synthesis, you have this carbonyl that's in the benzoic position, but you also have a nitro group on there. When you do this hydrogenation, okay, something will happen. You will not only reduce your carbonyl, you also reduce the nitro group. Oh, we already knew a way to do that, right? We talked about if you put a nitro group on the benzene ring, one of the synthetic utilities was what? To use stannous chloride, SnCl2. Remember, it reduced the nitro group to the NH2. So now we have another way of doing that. Interesting. Okay? And so that then brings us conveniently, now that we know a couple of different ways of doing things, now's a good time for us to kind of pause and talk about synthesis again. Because we know all these great reactions now. We know ways of adding substitute electrophiles onto a ring, substitute nucleophiles onto the ring, do oxidations and reductions on the side chains. We've learned a lot of new reactions. And so how can we then apply this all to synthesis? Now remember, those of you that were on the little Zoom meeting yesterday, I talked about the fact that when I do a synthesis problem, now I'm going to put up the synthesis problem, and I want you to kind of think about whether you can do it for a few minutes, but you need to hit the pause button because I'm just going to go immediately to the solution. So if you want to solve it on your own, hit the pause button. Okay, but I will set it up for you. What I'm asking you to do here, remember, is we want to make this compound from this one. So this is always the starting material. This is what you're trying to make. And so the trick on these syntheses, remember, is I need to figure out not only how to add these three groups, but I need to think about the order that they're added. So when you start your retrosynthetic analysis, the first question you ask is which of these went on last? Which of these three groups went on last? Okay, so I'm going to give you a minute to think about that before I do the answer. So now's where you would hit pause. All right, so the way to do this is which one of these went on last? Well, this nitro group is a meta-director, so it directs to these two positions. There's nothing there. This chlorine directs to the ortho positions and para. Okay. And this group directs ortho, para. So these two substituents direct the nitro group to that position. The nitro group doesn't direct anything else. And so therefore it's the thing that went on last, because these two substituents would direct it to that position. So that means that you're going back in your first step retrosynthetically to this, right? Okay, then what do you look at the same thing? Which of these went on last? Well, this one directs ortho-para. Okay, this one directs ortho-para. So neither one of these direct to the appropriate position. So what does that mean that I need to do? If neither one of these directs the other to the appropriate position, remember what we said is you ask yourself, can one of these be retrosynthetically converted to a meta-director? The answer is yes, this one can. If you convert that to the acyl group, then that would in fact, then when I go back one more step, I'm going to run out of room here, go back one more step, I would go back to the acyl group. Because if I put the acyl group on first, it allows me to put the chlorine in the proper position. Then I reduce it where it will then, both of these will direct the nitro to the proper position. And so do you see that analysis? Because that's going to be very common for the synthesis. Which goes on last? Which is directing to which position? Can I convert something to a meta director if I have my group's meta? And so that means the forward direction is to, I have 3 carbons, right? So you first do your Friedel-Crafts acylation. That puts the acyl group on. Then you do a chlorination to get this. And then you're going to reduce this. And we know several ways of doing that now, right? But now that we know that you can just simply do hydrogenation, instead of Clemenson, you can reduce to this. And then it's just a matter of doing the nitration. And you get that product. All right? So hopefully with the benefit of having these things recorded, you can go back and go through this thing a couple times if you need to. So let me give you another synthesis problem. And I think we're coming up with a good stopping point here in a minute. We just want to work through a couple of these synthesis problems. Let's do this. Let's put a branched alkyl group on here. Okay, and so we're going to make this from benzene. Okay, and so here would be the point. Remember, the strategy is to look at this and decide which thing went on last. All right, and then I'm actually going to not, you don't worry about pausing it, because I'm going to walk away for a second because I hear my dogs downstairs doing something. So while you're starting to work this, I'm just going to walk away and check on the dogs. All right, they're okay. So you can pause now if you need more time. All right, so how did we do this? Again, we looked at these 3 substituents and we asked ourselves which of these went on last. Well, this is an ortho-para director, so it would direct this group. This is ortho-para, it would direct this group, but the sulfonyl group would not. It's a meta-director. So it's the thing that goes on last, right? And so that would take me back to this. Right? And then, oh look, I'm kind of in the same position again. I've got 2 substituents. Neither one of them directs the other one meta. So I have to ask the question, can I convert either one of these into a group that would direct meta? And the answer is yes. You could convert this alkyl group into an acyl group. If you can't tell already, that's going to be a common theme. So if you learn that principle, it's going to help. So now I have that acyl group. Okay, so again, then what went on just before this? This group directs the bromine. So that means the bromine comes off. And I have my acyl group. And then that I know how to make from benzene. So the forward direction is to take your acyl group and your catalyst to do the Friedel-Crafts acylation, and then what am I going to do? Bromination, Br2, FeBr3 to get this, right? And then I can reduce this to get this, and then I do, now it's the sulfonation, which is SO3, H2SO4, and I get this product. Now, that was really kind of the same steps, and that's one thing that I hope you're picking up on, that remember I always say there are a finite number of possibilities of how the substituents are arranged on the ring and what your strategy is, okay? Because I can throw you a curveball here. I can erase this. And this is the kind of thing you want to practice in the home game with your friends. Because I can take this same structure and I'm just going to move one of the substituents. Okay? Now, how do you do this problem? Now, neither one of these directs meta. This is the thing that directs meta. Okay, so how are we going to figure out this problem? Okay, what we're going to do is, again, you can pause, but what we want to do here is, again, figure out what thing went on last. And I think when I worked it out, that the easiest thing to do was, we need to figure out a way of getting this group meta. And so what I did is I went ahead and said, let's go ahead and convert that alkyl group to the acyl group. Okay, and so our last step would be reducing that. And then that gives you this. Okay, and then when you go back one step from that, it's the bromine that gets directed meta by these two. So the bromine is what comes off. Like that. And then the acyl group would direct meta, and this would direct meta. But remember, you can't do an acylation if you have an electron withdrawing group. So you have to take this one off retrosynthetically first, because if you just had the sulfonyl group on there, you couldn't do a Friedel-Crafts to put this on. So that group had to have gone on first. Okay, and then we go back to benzene, which, even though I didn't draw it, was the starting material. So now going forward, I'll let you fill in the reagents, because they're just the same reagents we used before. So I would say that you need to spend some time working through synthesis problems like this. Just kind of move your substituents around the ring, and I'd practice with 3 substituents and just kind of get some strategies down on how to tackle different situations. Because again, there are a finite number of situations. All right, now there is one thing I want to conclude with, and that is this kind of topic we ran into on reductions. We had this compound at one point, and we talked about the fact that if I treated this with catalytic hydrogenation, it reduced both these groups. And we kind of said that as potentially a limitation, because what if you didn't want to reduce both? Well, with all of the techniques we know now, we have this neat little set of complementary reactions. Because yes, if I treat a compound like this with catalytic hydrogenation, I will reduce both of those groups. So I will end up with that product. But what was the other way that we talked about for reducing the carbonyl? Remember, we had the Clemmensen reaction, the zinc-mercury amalgam in acid. And when we did that, it reduced the carbonyl. But guess what? It does not reduce the nitro group. So if you want to reduce both, use the catalytic hydrogenation. If you only want to reduce the carbonyl and leave the nitro, use Clemmensen. And guess what? We also, remember, have the stannous chloride, the SnCl2, which we did remember in acid, followed by a basic workup. And that was what we used to transform the nitro group into NH2. And yes, it'll do that, but it won't touch the carbonyl. So do you see, with these three different synthetic reactions, we can get three different outcomes in reductions of this compound. So very synthetically useful set of complementary reactions. Now, according to my clock, I've gone about 52 minutes, but I think that we're at a really good stopping point here, because what we're going to do next time is we're going to start the chapter on alcohols, which begins with a brief discussion of organometallics. And so if you're doing any looking ahead, we'll be talking about alcohols probably the next two lectures.